Hi, I'm Mr. Parker and this is question 7 on the OCR Mechanics 1 paper from June 2010. For more questions on this exam paper, click the link here or check in the video description. A rectangular block B of weight 12 newtons lies in limiting equilibrium on a horizontal surface. A horizontal force of 4 newtons and a coplanar force of 5 newtons inclined at 60 degrees to the vertical act on B. In part 1 we need to find the coefficient of friction between B and the surface. So here is the diagram given in the question, and our first step will be to add on all the forces we have. In the question we're told we've got a weight of 12 newtons acting downwards. There'll be a normal contact force acting vertically upwards, which we'll call R, and there will be a frictional force opposing motion. And if the 4 newton and the 5 newton force are all pulling towards the left, the frictional force will be in the opposite direction trying to resist movement. So to find the coefficient of friction, we're first going to need to find limiting friction and the normal contact force. We'll start by resolving vertically, although it doesn't matter which one we start with. And taking upwards to be positive, we've got R plus a component of this 5 newton force, which will be 5 cos 60, and we're going to subtract 12 newtons because that's in the opposite direction. The block's in equilibrium, so mass times acceleration is 0. And if we rearrange this by adding 12 to both sides and subtracting 5 cos 60, we get R equals 12 minus 5 cos 60. Cos 60 is a half, so this becomes 12 minus 2.5, so we get R is 9.5. Next we'll resolve horizontally. Taking to the left to be positive, we've got 4 plus a component of the 5 newton force. In the vertical direction it was 5 cos 60, so in the horizontal direction it will be 5 sin 60. We've also got limiting friction in the opposite direction, and as everything's in limiting equilibrium, the right hand side will be 0. Rearranging this, we get Flim equals 4 plus 5 sin 60. If you wanted to, you could work out the value here and store it in your calculator, but there's really no need. To find mu, we need to use the fact that limiting friction equals mu r, and if we divide through by r, we get mu equals Flim over r. Flim is 4 plus 5 sin 60 and R is 9.5. And that gives us 0.877 if we round to 3 significant figures. As I've read ahead in the question, I know that I'm actually going to need this value later, so I'm going to store it in my calculator as A. In part B, we're told that B is now cut horizontally into 2 smaller blocks. The upper block has a weight of 9 newtons and the lower block has a weight of 3 newtons. The 5 newton force now acts on the upper block and the 4 newton force now acts on the lower block. The coefficient of friction between the 2 blocks is mu. Given that the upper block is in limiting equilibrium, we need to find the value of mu. So here is our new diagram, and we're trying to find the coefficient of friction between the 2 surfaces of the block. So we already know the coefficient of friction between the block and the floor, but as the floor is likely made of different materials to the block, the coefficient of friction between the 2 parts of the block will be different. So this time I'm just going to consider the forces that are acting on the top block. So we know there is a weight of 9 newtons pulling downwards. We also know there's a normal contact force like before going upwards, although the value of R will be different this time. And being as the 5 newton force is pulling to the left, we know that there is a frictional force pulling backwards that we can put acting just between the blocks here. So if we now just consider the forces on the top block, vertically we've got R going up plus 5 cos 60 like before, minus 9 this time equals 0. So very similar calculations to before. That makes R equal to 9 minus 5 cos 60, which is 9 minus 2.5 or 6.5. Resolving horizontally, very similar to before again, we're going to get 5 sin 60 minus Flim. Remember the 4 newton force is acting on the bottom block, so it's not relevant when we're just working with the top block. Again, everything's in limiting equilibrium, so that equals 0. So Flim equals 5 sin 60. Once again, we can use Flim equals mu r, so Flim over r equals mu. So we get 5 sin 60 over 6.5. And that gives us 0.666 if we round to 3 significant figures. Now I know we don't need this value later in the question because I've read ahead, but if you weren't sure, it might be a wise idea to store it as a different value to the last one, but I'm not going to do that because we don't need it. In part 3 it says, given instead that mu equals 0.1, find the acceleration of the two blocks. So as we do this part of the question, I'm going to use some subscripts to distinguish between forces on the top block and forces on the bottom block. So here, where I've put RT, that's just the normal contact force that's being applied to this top block. So the forces I've added to the diagram here are the same as in part 2, although this value for the friction here will be different because our coefficient of friction is different. And to find the acceleration of each part, we're going to work with each part separately. So first of all, I'm going to look at the forces on the top block. This is going to be very similar to what we did in part 2. Working vertically, we're going to have exactly the same thing. We would get RT plus 5 cos 60 minus 9. So when we solve for RT, we will get exactly the same as in part 2. We're also given the coefficient of friction between the two surfaces. I'm going to call that mu t, which is 0.1. That's going to distinguish it between the coefficient of friction between the block and the floor. I've used T here, by the way, to stand for top, and I'm going to use B later on for any forces that are on the bottom part of the block. So resolving horizontally with the top block, taking left to be positive, we've got 5 sine 60 going to the left. To the right, we've got Ft. We calculate F by doing mu r. Mu is 0.1, r is 6.5, and that's going to equal mass times acceleration. But remember, in the problem, we are not given the mass, we are given the weight. And we know that weight equals mg. So if we want to find m, we need to do the weight, 9 divided by g. So the weight of the block is 45 over 49, and the acceleration is the quantity we're trying to find. All that we need to do now to isolate A is to multiply up by 9.8 and divide through by 9. The whole of the left hand side will be the same, and if we put that into our calculator, we get 4.00 if we round to 3 significant figures. So that's saying that the top block, because of this 5 Newton force, will be accelerating to the left with acceleration 4 meters per second squared. We also need to have a look at the acceleration of this bottom block, and this is the tricky part of the question. Okay, before I move on to the next diagram, I want you to just notice a couple of things. First of all, we've got a normal contact force of 6.5 newtons acting upwards onto this block. It's not really coming out the top of it, it's actually due to the contact between these two surfaces here. We also have a frictional force acting on the top block, which is acting to the right. So when we look at our bottom block here, we need to keep them forces in mind. So now we're looking at just the forces acting on the bottom block. We can ignore this 5 Newton force up here. So we've got 4 newtons pulling to the left. We've got a weight force of 3 newtons acting down from this block. But as there is a 6.5 Newton force acting upwards on the top block, there must be an equal and opposite force acting downwards on the bottom block here of 6.5 newtons as well. And if you think about it, without this 5 Newton force, there would be a force of 9 newtons pushing down on this from the weight. But actually the 5 Newton force cancels out a little bit of that force. So we've got a force coming down here of 3 plus 6.5, which is 9.5 newtons. The block doesn't fall through the floor, which means there must be a normal contact force pushing up from the floor. This R here, though, is not this R. This R here is due to the contact between the two blocks, and the R in our diagram is due to the contact between the floor and the bottom block. At the moment in our diagram, we've got 2 forces pulling to the left, so there must be a resistive friction force which is pulling to the right between the floor and the bottom block. There's also one more force that people often miss, and that force arises due to the friction between the top and the bottom block. Remember when we were working on the top block, the frictional force was pulling to the right. So if the bottom block exerts a frictional force on the top block moving to the right, then the top block exerts a frictional force on the bottom block moving to the left. And I think in this question that's the tricky bit to get your head around. So I'd like to give a real world example that you can see that for yourself. If you imagine that you've got 2 textbooks on top of each other, and they're on quite a smooth surface, not completely smooth, just with, say, a low coefficient of friction, and you pushed on this top textbook to the left, if the floor is sufficiently smooth, you would actually find that both of the textbooks move to the left. And that's because the force that you apply on the top block, part of it will get transferred through friction to the bottom block here. Now that we've labelled up our force diagram, this question is actually quite straightforward. If we resolve in a vertical direction on the bottom block, we've only got R and 9.5, so we get R is 9.5. And you could, for this part, just resolve horizontally, and I'll talk about what happens if you do that later, but I'm going to do it a little bit different in the horizontal direction. First of all, I'm just going to consider all of the forces pulling to the left. So I've got this 4 Newton force, and I've also got this frictional force. Now I know mu between these two surfaces is 0.1, and I need to multiply that by the normal contact force between these two surfaces, 6.5. 0.1 times 6.5 is 0.65, so that gives us 4.65 newtons. Now I'm going to consider the resistive frictional force, and to calculate that I need to do mu r again, but with a different mu and a different r. If you remember back to part 1, I stored the value of mu between the surface and the floor as A, and that value was 0.876 and so on. So to calculate the resistive frictional force, I've got my 0.876 multiplied by the normal contact force here, which is 9.5, and that gives me 8.33 newtons and so on. But what you might notice here is that the resistive frictional force is greater than the pulling force, and friction only provides enough force to stop movement. So what we can just simply say here is that as the resistive frictional force is larger than the pulling forces, there just won't be any acceleration, so A equals 0. If you didn't spot to do this, it's no problem if you just resolve to the right, as long as you understand what you were doing. I'm not going to write it down, but I'll just do it in my calculator. My forces to the right, I've calculated them as 4.65. And if I subtract from that the 8.33, which I got from doing A times 9.5, and then divide through by the mass of this bottom block. Remember, we get the mass by doing the weight divided by G, so we would divide that whole thing by 3 over 9.8. And if you did that, you'd get a value for your acceleration of negative 12.0. And that's absolutely fine if you did them calculations, but you must, in the final step, spot that a frictional force can only resist movement and it cannot create an acceleration in the opposite direction. So if you got that answer and then said, therefore the acceleration is 0, then you would still get the marks.